Alright, so hi guys. This is going to be the second lecture in the neural network series, and in this lecture we're going to be talking about neurons, which are basically extensions of the perceptron idea that we talked about last lecture, and we're also going to be talking about hooking up these neurons to form neural networks, and then conducting forward propagation on those neural networks. So let's get started. These are credits, in case you want to find any of the images. So let's review the perceptron first. So if you recall back to last lecture, which was a while ago, remember that the perceptron is basically a weighted sum of all the inputs that we get into our perceptron plus a bias term. And when we view this in the two-dimensional sort of perspective, where we only have two inputs, x1 and x2, when we plot x1 and when we plot all of the sort of items in a data set and plot what the perceptron is doing, we can see that it's nothing more than drawing a linear decision boundary, right? It's just a line. And it's a line in 2D, but in higher dimensions, it's just going to be a plane. Uh, but the idea is the same. It's just linearly separating the data that we have. And just in case you may be confused, here we have axes, but actually both of these axes are independent variables in our problem, and the color of the dots are actually the output that we're looking for, right? So that's why I say we have two inputs, in case that was confusing. We discussed that last time too, but just remember that on this graph, these are both inputs. Both axes are inputs. All right, so basically, the perceptron can be depicted. This equation is basically just drawn out here, where we have two inputs. And in this specific problem, those two inputs would be like the coordinates of our dot. And then we pass that into, we conduct a weighted sum with each input's corresponding weight, and then we get a bias and add all those things up and then pass it through a step function. And the way we defined the step function was 0 if whatever the input is less than 0. And that basically represents all of the data points that are below our decision boundary, right? And then it's a 1 if the inputs are greater than 0. And that basically represents everything above our decision boundary. And so you can see that the step function, when drawn out, kind of looks like this, right? It looks like a step, and that's why it's called a step function. And so, these were great. And uh, in the last lecture, we also saw how we could combine two perceptrons to basically fit more complex data, and that was cool. But the main problem with this is that a perceptron can only represent linearly like linear divisions, right? It can only work on linearly separable data, where a simple a line can uh, correctly classify all the points in our data set. But that if you just stick with that, that drastically limits the amount of problems that you can solve, right? Because most problems cannot be condensed to these sort of like linear um, to a dimension where everything is linearly separable, right? Like most interesting problems, like if you're trying to predict whether a image has a cat or a dog in it, right? It's sort of hard to see how you could like maybe represent all those pixels, um, how you could represent the category of the animal in the image as a simple like linear combination of all the pixel values. Like most real world problems are not this easy, right? And so we need something else. And so that's where the neuron comes in. So the neuron is the exact same thing as the perceptron, right? We have, some inputs. Here we have n inputs, and then we multiply each of those inputs with some weight. We add a bias term and then sum everything up, and then we pass it through an activation function. The key difference between a neuron and a perceptron, though, is that this activation function is not just a step function, right? There's more complex nonlinearity functions that, when we apply them, allow our neurons to learn nonlinear mappings between our input and our output, whatever those may be, right? So just to make this clear, the only difference between the perceptron in the neuron is that we have this activation function, which we usually depict with a sigma, and that activation function lets us learn more complicated mappings between the inputs and the outputs. Whereas with the perceptron, we were only limited to a data that could be linearly separable. Okay, cool. I'll get into this very soon, but basically the idea is, once you have these neurons, you can sort of hook them up to form complicated neural networks that allow us to solve a bunch of different tasks. But first, let's talk about the nonlinearity functions. Here, I've just depicted a few of them. This is the sigmoid function. This is the ReLU or rectified linear unit, and this is the hyperbolic tangent function. And basically, there's like a whole host of different activation functions. These are just three, but the key thing to note is that the nonlinearity of these activation functions allows our neurons to represent mappings that are not strictly linear, right? And so when we do that, and when we apply this in our neural networks, we allow our neural networks to learn far more complicated relationships, and then we're able to solve a lot of the interesting problems that we really care about. Okay, so now let's get into neural networks. So as I mentioned before, we can just hook up these neurons together, right? And then when we hook things up like this, um, uh, depending on how deep our network is, like how many layers we have, and how many neurons we have in each layer, we can end up representing really, really interesting functions. And so this specific like neural network architecture, in the input layer, we see we have 784 inputs. And so this neural network is actually solving the MNIST dataset challenge, which you will get to do soon, where we have a 28 by 28 pixel image, and this is like a grayscale image of some number. And then we take each of the pixel values, and there's 784 pixels because it's 28 by 28. And then like we put the first pixel in this, we feed it in here, the second pixel here, the third pixel here, and so on and so on and so on until the 784th pixel, right? And once we have all those inputs, we can then feed those in to the neurons in this layer, and then as we go on and get to the final layer, once we train this neural network, which will be the focus of next week's lecture, this week we're sort of focused on representing neural networks, but once we train the neural network, we can actually get it to sort of light up the neuron that corresponds to the number that's represented in the image. So each grayscale 28 by 28 image has some number, and it's either going to be like, from 0 through 9. It's a one-digit number. And so, after training this, we can get this last layer of our network to light up the neuron corresponding to the digit that it sees, right? And so this is like way more complicated than the sort of simple functions that we were representing with our perceptron, and that's the reason why neural networks are so powerful. Um, so yeah. Um, so now let's get into, okay, once we have let's say we have already conducted backpropagation, right? That's the hard part. The hard part is training the network and getting the proper weights and biases. But let's say we magically have all that. Given some input, how do we actually pass the inputs through the network to get our resulting output, right? So let's say for this neural network, it's pretty small compared to the last one, but we have two inputs, right? Just two. So to calculate the output of this neuron, which we're gonna represent that output as N3. Basically, what we do is, we just do the weighted sum of all the inputs, right? So W1, 3 is the weight that's corresponding to this input and this neuron, and then we multiply that by input 1, and so that's all here, right? And we do the same thing for the second input, and that's all here. And then we add the bias terms. I haven't drawn in the bias terms here, but just know that they are there. Okay, and then, N3 is just the output of this neuron, right? And then similarly, N4 is the output of this neuron, and N5 is the output of this neuron. And this is the activation function that I was talking about earlier. And hopefully, this is probably going to be like some nonlinear activation function, right? And then we go through this network, and then N6 is the exact same thing, except now since we have 3 inputs to neuron 6, we have like 2 more terms compared to, one more term compared to the sums that we did for the previous 3, and that's it, right? If this didn't make sense, then just make sure to pause the video and understand this. Okay, so that was pretty simple, but it turns out that we can, if we represent the computations on the previous slide as matrices, we have several advantages. One is that if we have larger and larger networks, it becomes much easier to represent or like conduct forward propagation with matrices, both as a coder and for the computer. The reason why it becomes easier for the computer is because when we have a lot of matrix operations, multiplications, we can use graphics processing units, or GPUs. GPUs are actually like very popular in gaming, right? And the reason for that is that a lot of the a lot of graphics can be just represented as matrix transformations. But these are also exactly the same things that neural networks do. And so, okay, I kind of got ahead of myself there. But basically, if we can find a way to represent forward propagation as a bunch of matrix multiplications, then we can make use of graphics processing units. And that's exactly what people have sort of done, right? And so just to review matrix multiplication, let's say we have this matrix here. And so the dimensions of this matrix are 2 by 3, right? 2 rows and then 3 columns. And then the dimensions of this matrix here are 3 by 2. And so it turns out that since basically to conduct matrix multiplication, you have to have the same number of columns in the first matrix as number of rows as a second matrix. And then the output matrix, the dimensions of the output matrix will be the number of rows in the first matrix times the number of columns in the second matrix. And that's basically like said here, right? So if A is the number of rows in the first matrix, and then C is the number of columns in the second matrix, the final dimensions of our product matrix are A by C, where A is the number of rows and C is the number of columns. So in this specific example, since the inner dimensions match, since the number of columns in the number of columns in the first matrix match the number of rows in the second matrix, we can do matrix multiplication successfully, and the output dimensions of this matrix are going to be 2 by 2. And the way we do this is just you take each row of the first matrix and multiply by each column in the second matrix. And by multiply, I mean like the dot product. So you do 1 times 7 plus 2 times 9 plus 3 times 11, and you get 58 once you add all those up, right? Those 3 terms you get 7 plus 18 plus 33, and when you add those up, you get 58. And then to get the term here, you would do, you take this and then perform the dot product with this. So you get 1 times 8 plus 2 times 10 and 3 times 12, which would be 36 plus 20, which is 56, plus 8, 64, right? And you do the similar computations here and here. And so now that we know the mechanics of matrix multiplication, let's go ahead to figuring out what the vectorized form of forward propagation is, right? So in this picture, you basically see the equations that we came up with previously to represent forward propagation on this network, right? So we can basically represent this whole thing simply as this sort of matrix, this set of matrix multiplications, additions, and then we get all our outputs here. And so basically, this is our weight matrix that represents the weights of our that connect the input layer with the the hidden layer of our neural network, right? So each column here represents it corresponds to a neuron in the previous layer. So all of these weights are related to the input one, right? So this is the weight that's connecting input one to neuron three, the weight that's connecting input one to neuron four, and so on. And then each row corresponds to a neuron in our hidden layer. So both of these weights correspond to neuron 3, both of these weights correspond to neuron 4, and so on. And so when you do the matrix multiplication between this weight matrix and our input matrix, what you end up getting is, we can do this for at least n3. You do w13 times n1 plus w23 times n2. And then that's exactly what we have here so far. And then you add the bias term here. And then once you have that, you just put it all through your activation function. And that's represented by this, right? And so basically, the whole purpose of this is you get a vectorized form of forward propagation, right? Where once you organize your weights in this sort of specific matrix, then the bulk of your calculations are just matrix multiplications and then matrix additions for the biases, and then you just do you apply your activation function for every value in the resulting vector, and then you get this new vector that represents the outputs of this layer. And so more generally, you can basically formalize the forward propagation algorithm with this equation, where x I plus 1 represents the output of the I plus 1th layer, and then and these are just the weight matrices and the output matrices of the previous layer, and then this is the bias terms that correspond to the layer I plus 1, right? And then you just apply your activation function. Right, so as I said before, the advantage of doing this is that it really speeds things up, especially if you have a GPU. Okay, so we've talked about forward propagation now, so now we're going to get sort of closer to what happens, how do we actually train the neural network? And a lot of the back propagation stuff is going to come in the next lecture, but we're at least going to graze the surface here. Okay, so the goal of learning is going to be very similar to what we had in perceptrons, where we're trying to learn the optimal values for the weights and biases of our neurons. And so you might think, in order to improve our performance and get better on whatever task we're trying to do, it makes sense to quantify our performance, right? It basically give our neural network a grade, and then we can see what changes we can make in order to improve our performance. So the way we do this is by using error functions. And error functions basically take the current outputs that your neural network is outputting with the weights that you have, and then it compares them to the correct answers, right? So when you're doing a supervised learning task, where let's say you're trying to have a neural network that inputs an image of a cat or a dog, and then tell you is it a cat or a dog, then at every sort of step, you basically take the outputs of the neural network and compare it to the true correct answers, and then by putting all those things through an error function like the ones I've shown below, you would use this one for categorization tasks and this one for regression tasks, but basically the premise is the same. Once you once you calculate the error, you have a sort of metric to tell you how good or how bad your neural network is doing. And obviously, higher values for the error are bad, Yeah, and so you're trying to minimize the error. And so I was mentioning before that neural networks can be used for, actually, I don't think I mentioned this, but neural networks can be used for both regression and categorization or classification tasks. And classification tasks are sort of what I was talking about earlier with the numbers or the cats or dogs, right? You have like discrete groups. Um, so for the numbers, you only have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And your correct answer is going to be one of those 10 outputs, right? Uh, but on the other hand, neural networks can also be used for regression tasks. For example, if you're like given a bunch of input about some company, like their performance over the past few quarters, and then sentiment analysis, maybe on like tweets on the company, and you're trying to predict the stock price is like a continuous variable, right? There's like an infinite number of outputs that could be correct, basically, right? It's a continuous task. Um, so for those types of problems, you use an error like this, and then for other like categorization, discrete problems, you use an error like this. And so basically, as I mentioned before, the goal when we're training is to reduce our error so our network becomes less bad. So to do that, we perform a process called gradient descent. But before we get into that, we have to cover a couple of calc prereqs, right? And this is going to be like a really fast sort of. It's a review of the calculus for machine learning lecture, but definitely stop and then maybe review it from an external source if you're not familiar with this. Uh, and yeah, so basically, um, derivatives specify the rate of change of some function, right? Uh, for linear functions like this, the derivative is constant, right? It's always 2. Like rise over run is always 2. Um, for more complicated functions, like this is y equals x squared, if you imagine drawing a tangent line to a point in this graph, like let's draw a tangent line to the point 0, 0, right? The slope of that tangent line is going to be 0, right? You can imagine like it's just the x-axis. And then the slope of that line is 0. But if you move the x value, um, and then you try to draw a tangent line here, the slope is going to be positive, and here the slope is going to be negative, right? So derivative basically tells you the rate of change at a certain point, and that doesn't really make sense because rate of change implies that you're comparing 2 points, right? So that doesn't really make sense. But the way to visualize it is to imagine drawing a tangent line to a certain point and then thinking what is the slope at that point. So for this line example, like, it's always 2, right? No matter which point I pick on the graph, if I draw the tangent line, well, the tangent line is just going to be this line. And so the slope is 2. But here it turns out using something called the power rule, which you'll learn about if you take calculus, or when you take calculus, because in TJ it's required. Um, uh, Basically, what ends up happening is when you draw the tangent line, the slope is 2x, right? So depending on the, if you're taking the point, let's say 10 comma 100, right? Because this is y equals x squared, then the slope of the tangent line is going to be 2 times the x value of that point, or 2 times 10, which is 20. So in this function, the slope is constantly changing, and the way to determine the slope of the tangent line is to plug in the x value of the point that you're looking at. Okay, and we can basically extend this idea of derivatives to multivariable functions, where the output depends on more than one input, right? Here we have 2 independent variables like x and y, and then the output variable could be z. Right? And so with partial derivatives, basically what we end up doing is asking the same exact question as before, but since we have multiple input variables, when we are calculating like the tangent line, you hold all the other variables constant. So what that basically amounts to in 3 dimensions is taking a slice of the graph, and then doing the same thing as before. But you know, don't worry about that too much. Just remember that the partial derivative, um, it basically represents the rate of change with respect to one variable, right? Like if you have a multivariable function. Okay, so now that we know about partial derivatives, we can talk about gradients. The gradient is just a vector of all the partial derivatives of our function, right? And so the way you calculate it is you calculate um, the partial derivative of your output variable with respect to your first input variable, in this case x, and then you calculate the partial derivative of your output variable with respect to a second input variable, which is y, and so on. And you basically take the partial derivative with respect to every single input variable that you have. And it turns out that the vector that you end up getting basically tells you the direction of fastest increase of your function, right? So if you're at a certain point, what direction should I step in order to increase the output variable as quickly as possible? It's like if you're on a hill, which direction should I step in to go up the fastest, right? And so this is very useful for us because we have a very similar problem at hand, right? We are trying to minimize a function, the error. And the inputs to that function you can think of are our weights and biases, right? And if we somehow modify those weights and biases, we can decrease the error, and then get better performance on our neural network. Like that's what we're trying to do, right? We're trying to change the weights and biases in some way to decrease our output variable, which is the error, as quickly as possible. And so since the gradient represents the direction of steepest ascent, we just take the negative of the gradient and then move all of our weights and biases in that direction. And that ends up, by doing that, we can essentially train our network. This process is known as gradient descent. And on every iteration of gradient descent, we basically compute the the gradient of our error function with respect to like all of the weights and biases of our network, right? Um, and then whatever direction that vector specifies, we move in the direction opposite to that because, as I said before, the gradient represents the direction of steepest ascent, but we are trying to do the opposite problem. We're trying to move in the direction of steepest descent. Um, and so this sort of visualized on this graph here. Here we only have two input variables and then one output variable, right? So it's a greatly simplified problem. Even in the sort of small networks that we were viewing on previous slides, there were much more than two input variables. So this is like a very simple task, but the idea is very well communicated. Where if this is some error function, right? This is the path the gradient descent basically takes on every iteration, and you can see like it's changing the values of theta 0 and theta 1, which are the weights of this network, and then minimizing the error, right? And you keep repeating this process until you reach a point of convergence, and that's basically the way you mathematically like represent that is when the magnitude of the gradient it reaches some low threshold. Uh, Basically, your error function is flat. That's basically what that means. So one thing to note is that this process of gradient descent is not guaranteed to find the global minimum, which is sort of like the optimal set of weights and biases that you can have, right? It's not guaranteed to do that. You can imagine that, for example, if we started in this part of the graph here, by doing this sort of iterative like gradient descent, we could have gotten stuck here. But this valley is actually, it has a lower error, and so this would maybe have been, um, like a better set of weights and biases, right? So it can get stuck at local minimums, which are flat but not the flattest or not the lowest points on a graph. And so one question you might be asking is, why do we have to do this sort of gradient descent process? Because I mean, at least in the context of like a calculus class, you learn like how to find global minimums of a function, right? By like calculating the derivatives and then seeing where those are zero and so on. The problem is that this is quite hard for complicated functions, where like for a neural network, for the MNIST neural network that we depicted earlier, when you have like 784 um, just inputs, uh, there's a lot of weights and biases, right? Like thousands and sometimes even millions of weights and biases. And so the functions that you end up getting, like they're impossible to visualize, but it's like um, there's thousands or even millions of inputs to this one output value, which is our error, right? Um, and for those types of complicated functions, there's really no like easy, fast way to just find the global minimum. So iterative processes like gradient descent are necessary, and they're like the best sort of method that we have currently. And so, you know, the what I mentioned before hopefully all makes sense. But one question you may be asking is like, okay, how do we actually calculate those gradients? And so that's going to be the topic of the next lecture. And basically, there's this really clever algorithm, called backpropagation that allows us to uh, basically take advantage of the chain rule to compute uh, the the gradient of the like error with respect to all the weights and biases as efficiently as possible, right? And then once we have this gradient, we can just adjust all the values, as I mentioned before, and then keep iteratively decreasing our error. And so this is going to be the topic of next week's lecture. So hope to see you then, and thank you.